Okay, I think we're recording. Over to you, Julian.
Okay, thanks, Jonah. Right, hi everyone. Yeah, today I'm going to talk about some work we've been doing in the Trusted Services project related to firmware update and implementing components, reusable components that can help with adding firmware update capabilities to firmware in various forms. So, what's going on here? Sorry, I'm just asking it. So, here we go. Okay, so as I say, it's been added to the project. It consists of firmware components for implementing the update agent role, which is a role that's defined in an ARM specification to try and formalize the interface for that firmware exposes for submitting updates for various components within firmware. And the update agent is intended to be used with a third-party update manager living in the normal world somewhere. And the update agent deals with interactions with storage and with communications to the bootloader to tell it about updates. And so the core update agent supports the support includes an installer framework for allowing you to add different types of installers to handle different types of image installation. A sort of front-end interface component we call a service provider to allow the update agent to be remotely called across the normal world to the secure world interface, or potentially over any other kind of remote interface. Includes component integration level tests, and we have a reference deployment where the update agent runs within a secure partition, and an alternative deployment where the update agent is running in a command line application. And we're also working on wrapping the core of the update agent in a library to make it easier for downstream projects to reuse it. So features, it's about applying robust updates to firmware. So the idea is that the functions in firmware are essential for device operation, and so to reduce the risk of devices becoming unbootable, it supports an A/B update scheme where the active bank is never updated. We're always updating. There's always the ability to fall back to a viable version of the firmware. And it supports transactional multiple component updates where the firmware may consist of many parts and they can all be updated as a set. And so it offers sort of an all or nothing guarantee. And there's also the option for partial update support. So you might have firmware that involves many components, but you just want to target certain components for updates. The update model supports that, or it supports a complete firmware update. One thing that's probably going to be different across different platforms is the nature of the images, what format they're in. And so to accommodate that, there's sort of an extensible installer framework. So there's a general view of what an installer is, and contributors can add their own concrete installers to deal with different firmware image types. And it supports firmware that's distributed, could be distributed across different flash partitions, or it could be distributed across different actually subsystems. It has a flexible model for allowing for that. And there's this concept of a trial when a new update has been applied, and the ability to roll back to the previous version, either initiated by the bootloader or by the update agent. And there's also the capability to manage hardware anti-rollback counter to prevent rollback type attacks. Now, communications, ARM has produced a specification to help with compatibility between the update agents and bootloaders. And there's a definition of a data structure called the firmware update metadata structure, and the implementation conforms to that. And so the idea is that by with any bootloader, as long as it understands that metadata, we should have interoperability between the update agent and the bootloader. And there's also the specification also defines an image directory format, which is used to advertise the updatable components in the firmware. And that was specifically designed for easy interworking to the UEFI ESRT. But it could be interworked to other representations of the firmware as well. Okay, so there are a couple of important sort of abstractions that the implementation uses. It generalizes the view of storage via volumes. So a volume is an abstraction which it views as a unit of storage as being like a file. So it supports sort of byte-oriented seekable file type storage, and that could be mapped to a disk partition or any other kind of storage based on deployment needs. But the update agent just understands how to deal with storage volumes. And the storage volumes are used for accessing the metadata and for the firmware image storage itself. And we use the IODEV driver model that TFA uses behind the volume interface, and that allows drivers from TFA to be exploited. And so there are a number of different drivers there for different types of storage devices. Okay, so some examples of what a volume could expose. It could expose, a volume could expose an entire raw flash device. It could expose a flash partition or remote storage managed by a subprocessor, or it could simply be a file on a file system. But within the Trusted Services project, we've implemented a block volume, and that's compatible with the Trusted Services general view of a block storage interface. Okay, so that's storage, and another important concept is this idea of firmware locations, and so the view of firmware can be distributed across different locations, and these locations might be physically represented by a disk partition, for example. And a location is a useful concept because it allows us to bind together a pair of storage volumes, or as many storage volumes as you have banks for that location, and a set of installers that are capable of installing images into those volumes. And so we've got different classes of installer. We've got a whole volume installer, which updates the entire contents of a volume. We have a sub-volume installer, which will update portions of the volume. So that, for example, in the case of a volume that holds, for example, a FIP image, which is a container for multiple images, then a sub-volume installer would be capable of updating individual images within the FIP. But the installer framework allows you to define your own sub-volume installers to support different image formats. And we also have this idea of a copy installer, and that's used in cases of where there's an update that doesn't actually update a particular volume because it's only updating a subset of the images, and the copy installer can be used for copying from the currently active version to the updated version. And so a platform configuration consists of a set of volumes and a set of installers. And so platform integrators will be responsible for putting together those definitions to define this view of the firmware that the update agent will work on. Okay, so installers. So all installers will implement a common interface, and an installer is responsible for updating the target volume in some way. And that could be a very simple way. It could be that it just copies an input image to the volume, the target volume, or it could be that it updates parts of that volume. It's down to the implementation of the installer. Now, the installer presents a transactional interface, so it allows multiple images to be installed during a single transaction. And so, for example, there might be an update that's, for example, you have a capsule that might contain multiple images that need to be inserted into a FIP. And so a single FIP installer would be used to update multiple images within that FIP. And during an update, you could have multiple installers active at any one time. And so this is how the updates to distributed parts of the firmware are handled. So currently, we don't have many installers, but we have a couple of quite important ones. We have a raw installer, and that's the one that handles the whole volume installation. And we have a copy installer for copying from an old version to the new version. And we're very likely to add the FIP installer soon, which is going to support sub-volume installation into a FIP image. Okay, so that's installers. And so this is a picture that really sort of shows an overview of all of the components, and they're really separated into three parts. There's the core that we'd expect to be the same for any deployment. And so that has the common update agent sort of state machine and the logic that deals with a banked firmware store, and the platform specific part, which is a particular set of installers and a particular set of volumes that expose the non-volatile storage that needs to be updated. And then a front end that provides the interface to the update agent. And we have an implementation of that, which presents an interface that can be, that exposes the ABI that the firmware update A specification defines. But we can see that there'll be other front ends that will be needed for different deployments. Now, the core is going to be incorporated into a library, probably going to be called libfwu. And the idea there is that it will make it easier for downstream projects to reuse the core, to incorporate it into their own firmware. Okay. So communications with the bootloader is handled via a storage volume, which is actually a pair of storage volumes that the firmware update metadata gets written to. Now, the metadata structure is always written by the update agent, and it's read by the bootloader, by the early stage bootloader that is directed by the update agent to decide whether to boot from bank A or bank B, or for however many banks that you're booting from. Now, communications in the reverse, there is some communication in the reverse direction from the bootloader as well. The bootloader, having made a decision on what to boot, it's responsible for feeding forward the boot index, which bank it decided to boot, and also to feed forward the metadata version that it supports. And this is going to be useful in the future to add some resilience against incompatibility between the metadata version between the immutable bootloader and the update agent. And so this allows the update agent to respect the metadata version that the early stage bootloader supports, so that it can always direct the bootloader in a compatible way. The update agent maintains a replica of the metadata in a separate partition to defend against corruption of the metadata if a power failure occurs during update of the metadata. So the format of the flash, the update agent really doesn't care how it's formatted, but we do. The reference implementation assumes a UEFI formatted GPT flash with a GPT and a particular set of partitions. There's an assumption that there'll be a partition for the metadata, and then pairs of partitions for the other updatable portions of the firmware. And so this picture here gives an example of AB partitions for the application processor FIP image that TFA, for example, would boot. Another pair of partitions for the security subsystem, and another pair of partitions for the SCP. But the architecture is flexible, really, to support any number of different pairs of partitions. These are the things that map to this idea of updatable locations. And we include sort of automatic discovery of the partitions in order to configure the set of installers and volumes based on the definition of the GPT. Okay. So deploying where you actually want to deploy the update agent is going to be highly influenced by where the flash is that needs to be updated. And so there are probably quite a few examples. One would be you might have flash, which is dedicated to the secure world in order to protect it from access from the normal world, in which case the update agent would be deployed somewhere in the secure world. Now, reference deployment puts it in a secure partition. But you might have a single flash system where the firmware is booted from the system flash, which would normally be accessed by the operating system, in which case it would make sense for the update agent to be deployed in the normal world somewhere. So, for example, within a UEFI FMP driver, in a UEFI application, in an OS kernel driver, or even in the as within a user space process. So the idea is we've made the components as portable and as flexible as we can to make it easy for integrators to locate the update agent where it makes sense for their platform. So this is just a summary of where we've deployed the update agent within the Trusted Services project. So these provide sort of reference deployments, which give an example and hopefully can be useful in their own right. So we have a secure partition deployment, which will be suitable for platforms with secure world flash, where the update agent is accessed via the ABI defined in the firmware update A specification. We have a PC app deployment, where there's a PC app which wraps the update agent and it operates on a disk image file. And this is useful for testing, and it's useful as a tool in its own right for checking an image file and for applying updates and for updating the metadata within a disk image file. And we also have, or we're working on the libfwu, which is going to be a library deployment of it, which can be reused by downstream projects to wrap the update agents in whatever makes sense for their platform. There are also some test deployments. There are PC-based tests, which run through all sorts of update scenarios, testing the firmware update components that run in a native PC environment. And we also have service level tests that can run either on a real target platform or within a PC environment as well. So a little bit more about the PC app deployment. And so the update agent forms the core of just a command line application. And it operates on a GPT formatted disk image file. And so this would typically be a file that a build system, the firmware build system, would create. And then to actually check that, for example, your update images will update that successfully, the PC app can be used to inspect the directory contents, to apply the updates, and to check that after the update that the disk image file has been successfully updated properly. And it can be also used for tooling. If you want a model where the metadata is in a factory image is initialized, the PC app deployment can be used for writing the metadata within the metadata partition based on the contents of the GPT. But the way it works, I mean, it's exactly the same components as would be deployed in a real embedded deployment. And so the behavior will be exactly the same as on a real device. And this is another example of a deployment of where the update agent is running within SDMM. So this would be in a UEFI platform where it's desirable to communicate with the update agent via the normal UEFI secure, normal world secure world interface. And here, using lib FWU, the update agent can be reached via communicate calls to SDMM. So just a few words about testing. Most of the testing so far has been done within a PC environment. So we have a simulation of the device under test that simulates the device activation through restarts. And we have test cases that run through many different valid and invalid update scenarios to check the behavior of the update agents and that the updates are being applied successfully. And then we have resilience against things like power failures and other error cases. And we're also in the process of putting together some test infrastructure for some target-based tests. And this is the infrastructure we're heading for. And so the idea would be that we'll have test cases that run on a host machine and then operate on a device under test that can really be put through real restart activation cases. And so we can test the update in conjunction with the bootloader and confirm that the updates are all working properly. And with this infrastructure, we'll have access to the flat. In this case, we're using an FVP emulated platform. And then we'll have access to the emulated flash from the test case to allow us to inject error conditions, for example, corrupting the metadata or corrupting various images, and check that to check that the update mechanism is robust to that. And for getting access to the code, it's all under the Trusted Services project under the trustedfirmware.org. And some of the components used are reused from the TFA project, the GPT parser, and some of the low-level I/O device drivers are also from there. And there's a couple of other things we reuse from TFA. Okay, well, that's all the slides. So if anybody has any questions.
Hi, Julian. Yes, one question regarding this reuse from TFA, and that was mentioned also at the beginning of the slides. I wonder if it's, well, code reuse within the build, or if there is any binary interfacing with TFA?
Yeah, it's build time using. So what it does, we have in Trusted Services, we have this idea of an external components, and so we use some CMake facilities to allow us to fetch external projects, download them, and then to pick parts of them. And the way the integration with TFA works is that we represent components within TFA within the Trusted Services project to allow us to incorporate them into the Trusted Services builds. So the way we handle external projects depends on the project, and other ones that will actually use the external projects build machinery to build libraries. But for TFA, where it doesn't have those sort of facilities, we actually incorporate the source files into the Trusted Services builds.
Okay, makes sense. I had the impression that the IODev library was very much specific to TFA.
Yeah, it's been reusable. It was quite straightforward to reuse, and so I think there's scope to make reuse of some of the TFA components a little bit more straightforward. But I think actually TFA is really quite a valuable source of reusable components. It wasn't too difficult to do. There were a few little hoops that we had to jump through, but nothing too serious. But it's something we can think about, I think, in the future of starting to think what we can do to make components more reusable, because other projects can certainly benefit from some of the building blocks.
Yeah, sounds good. Good to hear, actually. Thanks.
Hey, Julian, Varun here.
Hi.
So just wanted to understand, you presented several scenarios for integration in multiple software components, multiple layers. So when you were designing this solution, did you interact with any of the actual device manufacturers or the final parties who are going to deploy this on their devices to, get inputs on the ABI interface, for example, or anything on the integration side that you had discussions with them that drove the design?
Yeah, so there were several. So I wasn't involved in these discussions, but I think, but we did have a lot of discussions about the ABI. And so this was the model that was exposed on the Secure World's Normal World interface, and how it would interwork easily with UEFI. So that's where the most of the discussions were. And I think there's also been a lot of work on defining the metadata structure to come up with something that would hopefully be pretty general and allow different bootloader implementations to conform to. So but that's where most of the work is. The conversations have been. The structure, the installer framework we put in place there was just to recognize, was really in response to the likelihood that for different platforms, there'll be a different view of what an image is and how it needs to be installed. And so this was really about trying to build in as much flexibility as possible to allow people to extend things in their own way to suit their needs without the reusable components getting in the way of that.
I see. So, one thing that I've also seen with these kind of projects, which can be used in multiple scenarios, is that sometimes there is some code that is not useful for one project. So can you talk a little bit about the configurability of the features in there, and if someone would like to trim it down for their use case, was there any thought process or any design discussions around that?
Yeah. Really the identifying what is the core and what is platform specific. And so the idea is that the trimming down would be about the kind of images you need to support, how distributed your firmware is, what it means to actually write to storage. And so so the idea is the core that doesn't understand any of that would be reusable, and hopefully reusable in all cases, and there wouldn't really be that much need for the configuration of that. And the configuration would be all in deciding how you interface to storage, how many storage volumes there are, what class of updates you need support, whether you want to support individual component updates or just very coarse volume level updates. So hopefully we've got the right balance between what's reusable in all or most cases and what needs to be specialized by platform. We'll see. I mean, we'll see as people try and use this. But that's the thinking, is to try and have a very clear separation between where you want flexibility and scalability and where you want something that's, where there's unlikely to be changes.
Right. And I think initially you also talked about interfacing with the storage drivers using a TFA provided API, the IO. Sorry, I forgot the name. But
yeah, the IO dev. I mean, that's an option. It's not the core. The update agent core deals with a pretty generic interface, this volume interface, which looks very much like a POSIX file interface on a single volume, and that can be specialized. That can map to whatever you need. And so I think that's a likely integration point for anybody who wants to actually use this on their own platform. They might have a completely different view of what storage looks like, but as long as you can represent storage as a volume, then it should be easy enough to plumb your own back end into this volume interface.
Okay. Sorry, one more question. So you had, I think you talked about boot components providing some information to the libfwu,
Yeah.
or for providing some basic information about the storage and where the images are located and all of that. So is that interface also standardized in some way, or and did you have discussions around that standardization also with the external party?
It can be handled in two ways, and so you're absolutely right. There needs to be a common understanding of what's an updatable image, where you find it, which is bank A, which is bank B, and the aspects of that problem that's been standardized is in an optional part of the metadata. So the metadata, which is about communications from the update agent to the bootloader, has got really two parts to it. There's the instructions that says this is the active bank, this is the fallback bank, and so there's pretty generic instructions to the bootloader about what to boot. And then there's an optional firmware store description, which is reflects the updatable images in an array of descriptors that says where those images are stored. And so it's in terms of the UUIDs of partitions and which one corresponds to bank A, bank B, or whatever. And so that's a way that a bootloader can understand the update agent's view of the firmware store. But an alternative would be that you would have the bootloader would have a common view with the update agent of the interpretation of a GPT formatted flash. And so you'd have common conventions for example, the partition type would be identify a particular image type. And then you'd have a convention for knowing which partition corresponded to a bank A and bank B. So it's kind of flexible as to how you achieve that compatibility. But you're absolutely right. You have to have compatibility.
Right. So as part of your project, have you also published the boot side of the code as an example somewhere?
Yeah, this is in TFA. So TFA implements the boot side of this, which is implemented in BL2, which interprets the metadata and boots accordingly and takes on the role of there are some error recovery conditions that it deals with. So yes, the reference for the boot side of that is in TFA.
Okay, thank you.
Okay.
I have a question: is what motivates you to use the GPT? And then follow-up question is if your updated firmware size is significantly larger than the original one, how you handle this kind of situation?
Well, the use of the GPT it's really not fundamental to the core of the update agent core doesn't understand anything about storage at all. And so the GPT use of that is just a configuration strategy. We had to choose a strategy, and we found that it's quite common certainly in UEFI based platforms to use a GPT formatted disk, but you don't have to. You can format, you can use whatever scheme you like to identify partitions. It could be device tree or whatever. So the core update agent is totally ignorant of how the storage is actually described. We just happen to use a GPT as an example, and hopefully it's going to be a useful example. But if there are platforms that use a different scheme, there almost certainly will be. That still makes the core update agent reusable.
Yeah, so that's why I have a follow-up question. Is because GPT was really designed for a large size, and then so how you handle if your updated fresh image is like way larger than the original firmware image size?
Well, in the case of the GPT, I mean the assumption is that the target volume for the update is big enough to accommodate your larger updates. And so the assumption would be, let's assume that it's a GPT formatted flash, that the set of partitions would be provisioned to be future-proof, to be big enough for any increase in size of the firmware.
Okay, I see.
Yeah.
Yeah, I think you probably can consider, if it's larger, and then I still don't see advantage to use GPT. But anyway, it's a random choice.
Yeah, it's exactly. You're absolutely right. I mean, it's you can use any format you like, and actually the constraint on the size of the storage is down to how you choose to manage your flash. And in the case of a GPT, then you are kind of forced into making the decision that your partitions need to be big enough. It becomes quite awkward and you have to resize partitions, but actually the update agent doesn't care about that. It just gets presented by the platform with a pair of volumes, and if it so happens that the size is managed in a different way, then fine.
Right. Thank you.
Okay.
I have one question related to the picture you showed about standalone MM, where we see that the agent is embedded into the standalone MM. Yeah, I wonder how this hooking is made, whether that's some build provided stitching, or if there is already an infrastructure within the EDK2 STMM to do this.
So this hasn't been done yet. So we're discussing this, and what's envisaged is that it would be built. Is that there would be an SMM endpoint that would be reached over MM Communicates with its own protocol ID, which would be for firmware updates, and it would handle call requests that map to the firmware update interface, public interface, and then that would be mapped to the lib firmware update library that would be incorporated into the STM image. So it would be a monolith.
Yeah, so I guess the MM communication is encapsulated into FFA in that case.
It's on whatever choice has been made. So that, yes, that would be an example. It doesn't really matter as long as you have the client that's able to talk MM Communicate over whatever lower layer calling mechanism has been chosen, then it should just work. The integration into STM would be at the SMM service level.
Yeah. Okay, I see. Thanks.
Okay. Of course, an alternative kind of related would be in the case of where your flash is only accessible from the normal world, is you could do something similar in an FMP driver that would run within the normal world UEFI firmware. That would make sense on some platforms too.
Okay.
Hey, Julian, Varun here. Sorry, it might be a naughty question, but just, my limited understanding tells me that STM already has functionality to update firmware. So, what additional features or what would be the motivation for folks to use libfw? Is there something extra that it offers, or I'm just trying to understand the advantages?
Well, it would be to support the sort of banked updates. If you need to support, have the flexibility for component-oriented updates and to have the AB updates, then it would make sense to deploy this in the STMM. I wasn't aware that STMM did support updates, actually. I might, that's probably my ignorance, but I think where it would make sense here is if you wanted the features that the update agent can provide in terms of A/B updates, multi-component A/B updates.
Pardon, a question on EDK2 supporting upstream updates from standalone MM. Is this upstream code, or is this potentially some functionality that's not currently upstream?
That's for the wider audience, Jose. Yeah.
That was directed at Vernon.
Yeah.
I was wondering whether the code that he was referring to is upstream in EDK2.
Yeah, no, I mean, I might be wrong here, but we have internal implementations that take care of firmware updates. So it might not be in EDK2, but if you look at the entire UFI story, firmware update story, then that takes care of updating the firmware on the actual on the target volume. So I mean, the placement might not be so in EDK2, but just wanted to understand how libfwu helps here.
The full integration that we would see, we've been envisaging, is that there would be an FMP driver in the normal world that would communicate via Communicate to the new SMN service endpoint for firmware update, which would handle the banked updates. And so the sort of capsule processing, the FMP capsule processing would be the standard EDK2 processing in the normal world.
Can you also talk a little bit about the complexity of writing these two shims around the library?
Yeah. So the bit at the top would be, so what's assumed is that the operations that will be reached over Communicate would correspond to the ABI operations. And so we have operations for starting an update, actually transferring the images, and then completing the update transaction. And so those will be reflected over the Communicate operations. And so this shim at the top is quite a thin layer that just terminates the Communicate calls and then maps them to the corresponding function calls in the libfwu. So that would be a very thin layer. The mapping to the storage would be about mapping this view of a volume to the EDK2 view of storage. And so again, that would be reasonably a reasonably slim shim. We already have a component that maps this byte-oriented view of a volume to our own view of a block device, which is very, very similar to the EFI block 2 protocol. So relatively slim shims, I think, in both the top and the bottom. But the bottom one is more dependent on what the actual storage arrangement is on the platform. But the top shim is certainly going to be very slim.
Okay, thanks.
Okay.
Thanks, Julian.
Yeah.
No,
Well, thanks for the questions. Thanks for the questions. That was really, really good. Thanks.
And I guess we want to plug the whole trusted services project. I mean, this isn't your only item. You've got other things, haven't you? And that can all be found on the trusted services homepage for the project.
Yeah. I mean, the idea is behind the project is that it's sort of like a toolbox of reusable components that can be used for implementing the various services that you might want to deploy in firmware. And so rather than having to rewrite them from scratch, we've got reusable components that can be used. And we've got reference implementations where these run in secure partitions. And so the firmware update support is following an established pattern for how we do that.
Thank you.
Okay, thanks, John.
So I guess we're coming towards the end of the hour, and this is the main session that we had today. I'm always on the lookout for other items to present. I think I may have a session for the next TFA Tech Forum in a couple of weeks, but I need to confirm that with the folks who are delivering that, so I won't quite announce it yet. But if anybody else has anything they want to share on these calls, please reach out to me. Okay. I guess there's nothing else on any other topics. If not, I'll end the call, and the slides and the recording of this session will be made available on trustedfirmware.org site in the Tech Forum session webpage for TFA. Thank you, everyone.
Thank you.
Thank you. Bye.
Thanks. Bye.
Bye.